So welcome once again to Zoom Seekers. And also thank you everybody for allowing me to move this up a day because I got Dodger tickets for tomorrow night. The game's starting at 6:30 and I don't want to have to choose between the two. So I hope you all understand and thank you all. As far as I can tell, nobody's wearing a San Diego shirt, so that's good too. In 1996, amazingly, 26 years ago, I got to do, when I was working for KCT, I got to do a dive on the Alvin submersible off the backside of Catalina, which what we called the show. We ended up doing a 30-minute documentary called Alvin and the Earthquakes, because part of the goal was to look for evidence of earthquake faults on the dive. Dive was down to 3,700 feet. And the geologist on that trip was this guy, Dr. Mark Legg, who I started calling Dr. Rock. And he was a big part of our show and educating me in various stuff. And he and I have stayed in touch over the years and talked about various geological stuff. And even at one point, we were doing a dive, as I sort of mentioned in the write-up for this thing, at Arrow Point. And I noticed there was like a whole portion of the bottom that was gone. And it was like a major underwater landslide and stuff like that. So he talks about, even though he's a geologist, geology does not just exist above the water. It exists underwater as well. And as you probably know, California certainly has plenty of faults, both the literal and the figurative, the geologic kind. But he's going to talk to us tonight about underwater faults and underwater geology around Catalina and whatever else he'd like to do. And Mark, I just want you to know, I wore this shirt because I decided the light blue, those are my fault lines on my shirt. So it's sort of a thematic thing here. So without further ado, let me give you Dr. Mark Legg, and please give him the traditional Zoom Seekers welcome. And I'm going to mute everyone's mics except for Mark's, and off we go. That's your cue, Mark.
Right. Did I share the screen, or is the screen shared?
You're gonna have to start the share screen again. It's not up yet.
Okay,
there we go.
That's it. Okay. Well,
there we go. I'll remind you guys, by the way, you have various options as to what you want to do. I'm gonna, on the view, I'm doing side-by-side speaker view. So all you'll see will be Mark. And I'll remind you too, there's a little on the right side of his share screen. If you cursor over that border, you should see two small white lines, and you'll get a double-headed arrow, and you can slide the picture left or right, make it as big or small as you would like to while you are watching. So Mark, with that, I will shut up and turn the floor over to you.
Okay, thank you, Ken. And like they said, we had a great time on that was the Atlantis 2 at that time from Woods Hole, and I was joking with Ken, and he said, well, be careful, Mark, because I can make you look really stupid on television. So so I had to cool it with some of the jokes I was trying to pull on it. But we had a great time. We had a great dive, and we got some good rocks. And this is the Alvin over here on the left side of the screen. I believe this was the new Atlantis, which came out a few years after that dive. And I've had the fortune to have had I guess 3 dives with Alvin when we dove with Oregon State. And I had a few dives with this Delta you see on the right. They're out of Torrance. We did some dives offshore. And then more recently with Scott Cassell, and they had an Ocean Gate program, which I got to dive at Catalina again. But a lot of my work has been done here with this group, and in particular, Mike Barth is a great friend. He developed this high resolution streamer. It's a bunch of connected hydrophones that we use to listen underwater to image what's below the bottom of the ocean, because we would like to know where the faults are, how recent they are, based on how young the sediments that are cut by the faults, and also to see the shape and things of the fault. So I've done a lot of that seismic reflection work for looking for faults, but also looking for things like paleo channels, like if they want to do a desalination plant, they would prefer to pull the water out of a paleo channel than directly out of the ocean. So let me move on from that. and get started with, am I doing this right away? Oh, okay. All right, so the very big picture background is here we are. And this is, I believe it's from the space station. Nice image of North America and what we like to call the Baja California microplate. So we've got the big picture plate tectonics is North America here in the Pacific Ocean, and the main plate boundary is the San Andreas Fault system, which goes through the Gulf of California and then on up towards San Francisco and offshore, at Mendocino. And the Baja California microplate is not quite on the Pacific plate. It's not moving as fast. The arrows are trying to show that. And in fact, even Guadalupe Island, and I know, Ken, I think you do dives at Guadalupe. Is that where you see the whale sharks, or is it the great white sharks? But anyway, it's not quite on the Pacific plate either. It's a little bit slow. And I'm convinced that's because this region offshore we call the California continental borderland, and the Baja microplate is putting drag on the Pacific plate so that it can't keep up, and it's actually causing it to be a little slow at this side of the Pacific. So we'll talk about that a little bit more later on, but that's the big picture. And here's zooming in. This is the California continental borderland. This part offshore Southern California, and don't forget it includes northern Baja California. In fact, beyond this image, all the way down to Vizcaino Bay. And this is a very special region that originally had been part of the subduction zone, but the pieces of the subduction zone, which included what was called a four-arc basin, which is like the Great Valley in California today, and this outer part, which was the accretionary wedge, where the sediments that were scraping off against the North American plate with subduction used to be. Well, that part of the borderland was down here off Baja, and the equivalent in the western transverse ranges had rotated. It was over here along the coast from essentially, LA to about Ensenada, which is about here. So you had major events in the tectonic evolution of this plate boundary. And this started about 20 million years ago when the western transverse ranges and then later the outer borderland rifted away. It was separated and created a big gap, which it made the crust thin and mantle could come up, and obviously a lot of faulting and even volcanoes came out. Now, what was interesting in some of my work at San Diego when I was a graduate student working with Francis Shepard, we were studying coastal erosion. So we were looking at historic documents and things. And we found this 1855 geologic map of Southern California, which was made for the Pacific Railroad Survey. And you'll notice they called it Earthquake Bay. And I thought, that's great. Oh, so why did they call it Earthquake Bay? Well, there had been a lot of earthquakes out there. And this was 1855. That was even before the 1857 big one on the San Andreas, the Fort Tejon earthquake. So here's a map showing the seismicity. These are magnitude 4 and above since about 1910. Now, it's not complete because they didn't have good recordings before about 1932. But there were two 1812 earthquakes in December, one in Santa Barbara Channel, which created a tsunami, which has been documented, but still somewhat controversial how big it was. But the second one was on the San Andreas here in Mojave, and it may have even broken off into the San Jacinto Fault here. But those were felt at the mission San Juan Capistrano and damaged it. In fact, it damaged it severely and collapsed the roof. And that plus the 1769 earthquake here was felt by the Portola expedition. And then in 1800, there was an offshore earthquake here that was felt. We don't know exactly where it was. And then 1862, well, that was after 1855. But that one we know about because there were some good records of that. And recently in San Diego, the San Diego State professor Tom Rockwell and his students actually found the fault rupture for that earthquake in San Diego. So we know where that one was. But you can see there's a lot of big earthquakes here on the San Andreas and these others, the Elsinore and the San Jacinto Faults. But offshore, there's a lot of earthquakes too. And there's even earthquakes way out here in the Pacific plate beyond the Patton Escarpment, which represents the former subduction zone. That's where the trench used to be. But these are out in the Pacific crust. And that was a surprise in December of 2012. This was about a 6.3 magnitude. And it had a mechanism which said that it was pulling apart orthogonal, perpendicular to these, which meant you're stretching the Pacific plate here. And I think that stretching is because this borderland sitting on top of the plate is causing drag. And as the Pacific plate moves towards Alaska, it's being stretched and breaks and earthquakes out there once in a while. So clearly, you can understand why they would call this Earthquake Bay. And this is just a refined catalog, which includes down to magnitude 2, where they could do careful relocations now with digital seismometers and computer technology and so forth. The red dots or circles are pre-1981 because they didn't have digital recording until 1981. But still, you can see clearly where the major faults are. Here's the San Clemente Fault offshore, which is my favorite. This is the one I've been studying most enthusiastically. But there's this 1986 sequence offshore Oceanside. Some of you may remember. Aftershocks lasted 10 years. The Long Beach earthquake in 1933, famous on the Newport Inglewood. Out here, the Elsinore, the San Jacinto, and the San Andreas. Down here, it would be the Imperial Fault. But not much on this part of the San Andreas, but then a real complicated mess where the Baja California Borderland microplate is crashing into, it's a big collision zone like India colliding into Asia here in the transverse ranges. Then, of course, the San Andreas goes off to San Francisco. This one here in 1927, Point Arguello earthquake is the largest offshore earthquake recorded on seismometers. It was about a 7.1. And it did create a tsunami that was about 6 feet high over here on the coast at a place called Surf, which is a railroad siding near Lampo. And it was also recorded on some tide gauges in San Diego and places. Just as a historical fact, when California became part of the United States, the first thing they did was put a tide gauge in San Diego and a tide gauge in San Francisco, so the ships would know what the tides were, because those were the major ports at the time. Those tide gauge records actually have shown some very important records of tsunamis over history. Okay, so we're going to talk a little bit about, how do we find faults in the bottom of the ocean? What's underwater? And so we're going to try to do like they do on land. Usually the first thing they do is try to find these landforms, the morphology, the shape of the land. And this was produced by a US geoscientist, Malcolm Clark. And it's really a great diagram. But under the sea, the easiest things to see are things like these pressure ridges, because it pushes up very linear ridges. Linear features are particularly important to recognize faults because they tend to be relatively straight. You also have the scarps, where you have the steep slopes on the edge of uplifts. You have these hillside valleys where next to a ridge, there's a valley which is very straight. Those are the main things that you can see just by really good mapping of the seafloor. Of course, we didn't have really good mapping of the seafloor until the last couple of decades when they finally invented the multi-beam echo sounding system. And with that, we've made great strides in mapping the seafloor almost as accurately as they did with the space shuttle and when they did the topographic mapping of the whole Earth or whatever. The other thing is these springs, these seeps, and they come up along the faults. And those have been a lot of interest. A lot of more recent cruises, and especially with submersibles and ROVs, have been going down to look at these seeps because you have all sorts of different fluids, methane, and some we saw on the San Clemente Fault, and others there's barite that comes out, and they may be where the fluids that make manganese nodules come out. Those are also good evidence that you've got faulting in the area. So those are the kind of things we want to look for in the topography on the seafloor. Now, interestingly, the first fault identified in California was the San Clemente Island Fault, because California was explored from the sea before they really got on land, and they recognized these steep slopes here, the escarpment on the northeast side of San Clemente Island. And you can see the clouds. This was taken in March of 1998, and Charlie Hollister was the chief scientist at that time. You've heard of the Hollister Ranch? Well, he grew up on the Hollister Ranch, and when I met with him in Woods Hole, he was showing me the saddle he had when he was 10 years old, the saddle he had when he was 15 years old. But anyway, we had a great time on that cruise. Unfortunately, the weather was kind of nasty. We wanted to dive south of here at a place that I'd been with the Turtle, the deep submergence vessel Turtle with the Navy in 1989, but it was too windy, so we had to wait 18 hours to get permission from the Navy, because San Clemente Island is Navy territory where they do a lot of bombardment practice. Anyway, so we're here in the lee of the island getting these multi-beam sonar profiles along the San Clemente Fault. Now, after that time, that was in 1998. In 2003, the Navy went out with their ship, and of course, they have top in the systems, and they got this fantastic high-resolution bathymetry around the island. And I think you can see a fault going through here. In this area here, we've got all these gullies are offset. It's like the Carrizo Plain on the San Andreas Fault. But up here, you can see the fault makes a little bend. And so here you've got folds where it's being squeezed, and you've got a very straight, and the slopes just get cut off. And on this Emery Knoll, this big feature here, that end is cut off and dropped down in what we call the graben. So that's extensional. And that is direct evidence that this fault is a right lateral strike slip fault, which means this side towards North America and the coast moves toward the south towards Baja, well, with Baja, and this side to the west moves to the northwest with or towards Alaska. And this dashed line is based on the best plate tectonic models of what the plate motion between North America and the Pacific plate should be at this latitude. And you can see the San Clemente Fault is parallel to that. So the San Clemente Fault is one of the major transform faults of the Pacific North American plate boundary. And this, to me, says this fault is very active. And of course, we saw all the earthquakes previously. So this is pretty exciting data to get. And again, my colleague Jason Chater, he was an Oregon State PhD student, did his work on this fault farther north. He's now at the USGS at Woods Hole. So we got out there more recently. The Nautilus was out here. This is Bob Ballard's group, the Ocean Exploration Trust. And they were out here for about 5 or 6 years doing work off California. And I was fortunate to be involved with a bunch of dives. And they had the Hercules here, which is the ROV, and it has a little intermediate, I think it's the Argos, which they hang from the ship so that it can absorb the ship rolling and moving up and down and keep the Hercules at a very stable position as it explores the bottom. And they also have, I guess it doesn't show on this picture, they have a satellite dish on it so they can broadcast directly to people all over the world to watch and take part in the dives. And so that was a great opportunity, that website down there. They're off Hawaii now doing a lot of work out in the Pacific along the seamounts and stuff. So here's some work, and this was done with some of the work we've done with the early multi-beam mapping with Oregon State, combined with the data that had been accumulated in the first several years of multi-beam bathymetry. And we're looking north along, the San Diego Trough, north 30 degrees west, which is the trend of the San Diego Trough. And there's a fault that runs through here. And that comes and then it curves around. You've got the San Clemente Fault over here, which comes and it steps to the right. And for a right lateral fault, this is moving south, this is moving north. So when it steps that way, you create a hole, which is a basin. And up here is San Clemente Island. You can see that bend we just talked about, and that's the part that's constrained, so it's pushed up. And this part's the part that's sort of extensional. Emery Knoll is that feature, which thing is. And Emery Knoll is this chain of craters. You can see this circular pattern. I mean, the morphology gives you so much information. And on the seafloor, it's not overrun with off-road vehicles and all sorts of other things. So you can still see what was created by Mother Nature, earthquakes and faults and so forth. So we got a chain of huge craters here. This is 26 kilometers across. It's as big as the entire Los Angeles basin. So imagine a volcano that big. And this one, Emery Knoll, is another one. And the rim of this one has been offset. It's up here, offset 60 kilometers by the San Clemente Fault. So that means this fault's moved 60 kilometers in the last 15 to 20 million years since that volcano was active. And the smaller one, Navy craters down here. And of course, the volcanic deposits from these, one thing you need to understand is when the outer borderland out here beyond this red line, when it moved away from the coast, it created a rift. And this is what came up in the rift. And you had a chain of volcanoes in the middle. So these volcanoes were erupting over here on the coast. And you can see the lava flows from these volcanoes when you drive to Ensenada along the coast highway here in Baja. And you can imagine that would have been a really exciting time when these blew up. I mean, these are bigger than Krakatoa. They're more like the Tambora or the things that destroyed the Minoan civilization in the Mediterranean Sea. Of course, here's the Spanish name they had for Bahia de los Temblores, which is our earthquake bay with Los Angeles up here and San Diego down here. The other interesting thing is you've got major submarine canyons. Like this is the Coronado submarine canyon just north of Los Coronados. This is Coronado Bank, Point Loma here. And that canyon cuts through this ridge, which formed during that extension. It's a tilted block of crust that tilts down to this side, which makes that steep slope. But this canyon goes down, and you can see it runs into something here. And so it meanders here until it finally gets around it and then goes down here. Well, that's the San Diego Trough Fault, and it's pushed up. There's a slight restraining band here, which is pushed up crust that blocks this canyon. So these are the features we can use to recognize the faults and hopefully someday identify offset features and get the age so we can figure out how fast this fault is moving to understand how often we'll have large earthquakes on that fault. Then it goes all the way out here, meandering all the way until it finally gets through this gap between this ridge, because this is the ridge that came up in the rifting. These are the deep basement rocks which you see exposed at Catalina Island. They used to be underneath Coronado Bank and underneath the coast. They were literally pulled out when the subduction stopped and the Pacific North America plate boundary formed. And so there's a lot of interesting stuff over here. And in San Clemente Basin, we're going to talk a little more about this area. This is Navy Bank, and this is the Navy Fan. We'll get into that shortly. But another curious thing, this little ridge, and with the multi-beam data, you can see there's sort of an arcuate shape to this part. And if you move that back, it fits in to fill in the rim of Navy Crater. So there's what we call a piercing point, which says there may be 30 to 40 kilometers of slip, not only the right lateral slip moving south, but also the extension moving over from that rim. So there's something that gives us an idea on how this part, how the San Diego Trough actually widened during that time 10 to 20 million years ago when it was rifting apart. Nowadays, it's mostly strike slip moving towards the transverse ranges, but because of this blockade, there's a lot of these uplifts because it's a collision zone and they just don't have room, so they're going up. So I'm going to talk about restraining bands. I've mentioned these before, but in particular, here's some high resolution, actually very high quality, high resolution sub-bottom, seismic profiles that we got on a student cruise with the UC Santa Barbara back in 2003. And this is the San Diego Trough in that area we were looking at. And there's what you would expect a strike slip fault to look like in a seismic profile. If you did a cross section, you can tell these layers are the same as these layers, but they don't quite match because these are a little bit thicker and they're a little higher. And that's because these have moved from the south into this area next to these, relative to this side of the plate, on the Coronado Bank side of the plate boundary. And so that's classic example of what a strike slip fault should look like. But that very same fault about 6 kilometers north of there, so that's about 4 miles north of there, goes through a small bend. The bend is only 5 degrees, a very, very slight bend, and yet you produce 700 meters. So that's about 400 feet of uplift. Just do that little bend in the strike slip fault. And that's something you need to remember. A little bend in a strike slip fault makes a big bump. And we'll talk about that when we talk about the Palos Verdes Hills and Catalina Island, because those are really big bumps that have formed in that same process. But again, here you can see these same sort of sequences, but they're farther north, so they're thinner because they're farther away from the submarine fan, which is on the Baja California coast. The multiple is just the echo of the water bottom, and it wraps around because you record in time, and that's where you see it again at the top. So this is the kind of information we like to really see that this is a steep fault, as most strike slip faults are. Mechanically, it's easier to move sideways than to move together or apart. If faults that move apart or together or together push things up, they often form faults that dip. They have an angle from the horizontal that's not vertical because it's easier to push things up a ramp than it is to push them straight up. But as you can see, you can have a vertical fault and it still pushes things up. It just creates a fold. In fact, there's a fold on both sides, and you have to remember again, this fold actually came from the south compared to this fold as well. The strike slip is there, and a lot of people that look at two-dimensional cross-sections like seismic profiles forget there's a third dimension here, and of course you have to think about the timing as well. So a really good structural geologist has to think in 4 dimensions. So here's another place where we have a little restraining band down here we call Catalina Island, which is actually a pretty big restraining band. And it goes to another ridge, which is a little bit oblique to the plate motion, so it's been squeezed up. And we have the San Clemente Fault comes through here. This is the eastern branch coming off of San Clemente Island, which is just below the picture. And the Catalina Ridge Fault there on the northwest side of Catalina, north of Little Harbor, it comes along that ridge. But you can see there's a triangular zone here, which seems to have slid along that fault into here. But and there's a hillside valley because these two faults are interacting. And we had this earthquake sequence. This is the 1981 earthquake. It was about a magnitude 6, that some of you may have known or felt. And this is a cross section of the epicenters for the aftershocks and the main shock. Down here's the main shock. And the black dots are the ones that are the most accurately located, and the red ones are a little bit less, and the open ones are not as good. But you can see that this fault down to 20 kilometers, or at least down to 15 kilometers depth in the crust, is essentially vertical. But there's not just one fault, it's a zone. The main shock was probably on this fault, which, as you can see from this line of these dots, these are those well-located epicenters. Well, that's over here, not where I'd mapped the fault here through this hillside valley. So this is what is the east branch of the San Clemente Fault from San Clemente Island, whereas this is the Catalina Ridge Fault, which comes along the west flank of this trough. And you can see it's a very linear trough. And it's, of course, even more complicated than that. These focal mechanism diagrams we call beach balls, and the black side, it's moving towards the black side and away from the epicenter on the white side. So this is moving towards the southeast on the east side and towards the northwest. So that's a right lateral strike slip fault. In a cross section, that same diagram projected is showing a vertical fault, with this side moving towards the plane and this side moving away. Is that right? Yeah. So anyway, the main point is here, these main strike slip faults, which accommodate most of the slip towards Alaska, are vertical because it's more easy mechanically. But because of the complications of the transverse ranges and all the faults, we get a lot more complication of faults. And fault zones in general are not nice, simple planes, but they're zones. Oh. Yeah. So the other thing was that looks very much like the intersection of the San Andreas Fault with the San Jacinto Fault, where those big 1812 earthquakes and 1857 earthquakes occurred. So we might be considering about earthquakes in this area even larger than magnitude 6 at some time in the future, and likely in the prehistoric past. So here's again those epicenters along the San Clemente Fault and the ones here over on this branch falling from the Catalina Ridge. But this is what we were able to do with the detailed multi-beam echo sounding of the exploration vessel Nautilus. And then with the ROV Hercules, we went down and did some dives here to look at these scarps and to try to see what's along this. You can see this sort of bluer segment with the purple's deeper than this blue. So there's a pressure ridge here. So when you squeeze, when the fault moves, it breaks up the rocks and that creates space. So it squeezes it up, forming a pressure ridge. And that was in there, so we could see that. So here's what we saw from the Hercules ROV. Now over here is just to show you in some real earthquakes. This was a magnitude 7.5 in Alaska on the Denali Fault. You can see this really jaggedy rupture, but there's a pressure ridge. That's a pretty big pressure ridge, these people for scale. And here, this is a famous picture from the 1906 San Francisco earthquake on the San Andreas Fault, and that's what we call a mole track. It's like a giant mole had been burrowing along. These are classic features that show, what happens after a large earthquake. Well, we're seeing that here. There's you can sort of see the jaggedy character here, and you've got the little step. So this is a scarp, but you also have a seep because all of these, these scallops here and these other critters are feasting on that mineral-rich water coming out of the seep. So it's a very popular place. And it was great because, we're geologists, or I'm a geologist, and you think, the biologists don't care about the geology. But actually, they said, we're glad you geologists are here because every time we find rocks, we find the most interesting creatures we've never seen before. And we've seen some very exciting creatures on those dives. I don't know if you remember the purple squid and the purple bollard. Some very interesting creatures that, like I said, they'd never been seen before. And all those samples went to the Harvard library where they keep those samples for logging and for future research. Anyway, so this is the view from the Argus looking down at the Hercules down here on the bottom, but you can see this sort of straight line. It's kind of crumbly and stuff, but that's the fault scarp. And I don't think this was the fault scarp from a magnitude 6 earthquake. This is probably an older fault scarp from prehistoric earthquakes that were somewhat larger to create that much offset. But again, We don't know. It takes a lot more information, a lot more detailed study to get that kind of detail. But this is what we got, again, with a high resolution seismic reflection profile going across that hillside valley. So here's the scarp, and this is only a 1.6 vertical to 1. So that's still probably a 20 or 30 degree slope. That'd be a steep climb. But here's the main fault, the one that ruptured in that earthquake. And you can sort of see here, these things are offset in this area. It's a little harder to see in the shallow water, but here in these nice sediments, you can see all these faults coming in this zone in the hillside valley. And here's the pressure ridge, which pushed up. There's faulting in there. And this they tend to call flower structure because it sort of flowers out. The fault down here seems to be more narrow, and then it spreads out because the pressure is less, and so it can spread out and push up the pressure. But here's an even larger pop-up where you pushed up these would be like 15 to 20 million year old rocks, and then up here probably 10 to 8 and 6 million year rocks, and then you might get up to some that are only a few 5 million years. But on the top here, you've got the youngest ones. And the rocks in the, since the glacier, these are rocks that came in the glacial times. So they're not as thick. But you can see that these older sedimentary rocks at the bottom of the ocean, which filled that basin that formed during this evolution of the inner borderland rift, we call it. Well, those are the sediments where all the oil is that they get in Los Angeles, but also the diatomites and all sorts of interesting minerals and creatures are in there. But they've been squeezed up due to the irregularities of the fault not being perfectly straight to form this hillside valley. So it's a broad zone. It's more than 3 kilometers wide. On land, the land geologists will do a trench across the fault, and they may do it 100 meters across. Well, this is 3 kilometers. That's what, 300 times. So they don't do trenches that long, and so they're missing a lot of the faulting. But they do get, they do focus on the main faults like the San Andreas and San Jacinto and get the main slip. But again, fault zones are complex. They're not as simple as people think. So just a quick look back, there's the earthquakes with some other focal mechanisms. And you've got the strike slip ones here. This is a thrust fault earthquake, which is on the Palos Verdes fault. There's another thrust, which was the Oceanside earthquake in 1986, but there are also strike slip earthquakes there. Here's another thrust over here, and there's thrusts here on this east-west ending because this part's trying to get to Alaska, but the ridge at San Nicolas Island is in the way, so they're thrusting, pushing up that ridge. And you get thrust faults, especially up here, well, like the Northridge earthquake and the San Fernando earthquake in 1971. Those are the thrust earthquakes in the transverse ranges because Baja and Southern California is smashing into the transverse ranges. I'm just going to show some examples from the Nautilus and the Hercules dives at Trask Knoll, which is actually quite similar to Catalina, a little smaller, but it's got the Catalina schist type rocks at the surface. We're going to look, we were just looking at this area, which is the Hillside Valley on the Santa Cruz, from Santa Cruz Island to Catalina Ridge. And then we're going to way out here in the southern borderland. This is actually it's in U.S. waters because the boundary is right here. So it's just inside U.S. waters because there's a 200-mile exclusive economic zone, which has sort of a weird shape because it's halfway between the islands and so forth. But so this is just inside U.S. waters where they were able to dive those cruises in 2016. This is that 6.3 earthquake in 2012. And you can see the motion was in that direction, which is the direction the Pacific plate is moving towards Alaska. And that's extensional, which means it's pulled apart. So it's that's my working hypothesis, that's being stretched apart and breaking in these normal fault earthquakes. And this one has one fault plane which is almost horizontal and one which is vertical. Okay, so this is Trask Knoll, and there you go. It's sort of a rounded rhomboid shape, which is typical of these pop-up structures where there's a bend in the fault and it pushes up things. And you can see this pressure ridge, which is the main fault, and scarp on that side of it. And way out here at Southwest Basin, because up here, Lake Knowles are south of San Clemente Island, and 60 Mile Bank is 60 miles from San Diego. But you can see there's another pressure ridge there and big scarps. And here's the area on the pressure ridge at Southwest Bank. And you can see that pressure ridge with the high resolution bathymetry we got with the Nautilus. Very interesting. It's got some curves in it. So it's got restraining bands where it pushes up, and we've got little step overs where there's a little basin. again, this is a right lateral fault that has some convergence, and a bench, and then a major scarp, which is southwest bank. And this is the scarp with the rocks. You see the very straight line here. So that's probably an ancient fault break from a prehistoric earthquake. And these are boulders, and these look very volcanic, but you got to be careful because sometimes, well, a lot of rocks look dark on the bottom of the ocean because they're covered with biological material, or there's geochemical reactions, things like manganese nodules and stuff, which turn the rocks dark. But these, I think, in this case, actually are volcanic. So here is Trask Knoll in a little more detail, and you can see that pressure, it goes for miles as that fault continues beyond the knoll. And this is a close-up of that, again, with the high-resolution bathymetry from the Nautilus. And there's a bench. You can see the profile across of the fathometer that shows us a little peak and then the bench. And this is the scarp on that fault. And it's covered with creatures. And of course, the biologists are having a good time because they're finding all sorts of creatures. Some they've seen before and some they haven't. Looks like there's, oh shoot, is that a rock? What's that? Yeah. Well, I'm not a biologist, but I remember there's a lot of these. Well, anyway, I'm sure some of you know. It's related to lobsters, but it's sort of long.
It's a crab of some sort.
Yeah, it's a crab. It's that long, skinny one. And I used to remember the name, but anyway. All right. So once again, I'm going back to this view, and there's, just so you'll know where you are in the world again. We're looking north along the San Diego Trough Fault, and it's going through here. And out here, we're going to be looking at Navy Fan now, and it's Navy Fan and Navy Bank. And why is that? Well, Navy's at San Clemente Island. This is their gunnery range, and they're always out here doing operations. So these are Navy Bank and Navy Fan. And anytime you do work here, you have to get permission from the Navy. So you have to work with them because you don't want to be working around San Clemente Island where they're doing bombardment. I think there was a fishing boat back here one time that actually got hit one time. That was 10 or 20 years ago when I was living in San Diego. I remember that. So anyway, we're going to go focus here at Navy Fan. Again, this was my colleagues at Oregon State, Jason Chater, who's now with Toll, and Chris Goldfinger. And Marta Torres was chief scientist for this cruise. And Marie D'Angelis was from Humboldt State University, and their focus was the seeps. So we're going to Navy Fan because Peter Lonsdale from Scripps got a free ride with the Navy on the senior moment. Anyway, it was a submersible that was Alvin before, but then it changed. And he got a free dive, and they went here because some work Scripps had done on the submarine fan here was Bill Normark's thesis area. Bill Normark was at USGS, an original Scripps student. They found a scarp here, and Peter Lonsdale got a free ride with the Navy to go down the submersible, and he found 60-degree slopes. That's really steep slopes, and so they knew there was a fault there. So we got to go there, and he also saw the barite, and he saw the clams and the bacterial mats and all the things of classic seeps. And when he did that in the 1990s, that's just when they were discovering hydrothermal vents on the East Pacific Rise. And they finally showed that there was hydrothermal activity on Seafloor at Seafloor Spreading Center. So Peter thought they were hydrothermal at first, but later they've been found they're actually cold seeps. And these cold seeps are all over the borderland. So we went there to look at those. And this is a detail of the map of this big restraining band on the San Clemente Fault. And you can see the fault sort of wiggles around through here, but it's great. You can see the faults in the bathymetry offshore. And here where it bends a little bit to the left, it pushes things up. It steps a little to the right, it creates a little basin. It bends again, it pushes it up. It steps to the right. And in this pull apart, it's 6 kilometers long, which is 4 miles. The people from Imbari did an AUV survey of this, and they said they've seen more seeps in this little basin than anywhere else in the world. That's, of course, there's a lot of ocean out there that's never been explored, but still, this is Seep City Central or whatever. And then it bends again to make this pop up, and then it steps over into this big basin, and there's this little scarp, which is where Peter Lonsdale got his dive, and this is where we went with the Alvin at Navy Fan. Of course, here's the Submarine Canyon, Fan Valley coming around and then shooting down between these ridges. So it's interesting, the bottom of the ocean, these valleys meander just like the rivers do on land. And because this is actively growing with earthquakes and tectonics is pushing up, this channel keeps getting pushed farther seaward, and you can see the abandoned elevated terraces along the flank. And this is tectonic geomorphology on the seafloor. It's fantastic. And you can tell I get a little excited about it. You can see there's another fault over here and some more faulting. These features are the edges of C-beam swaths, so they're kind of noisy, and that's, you have to be careful with these things which are related to edges of swath tracks. But as we get more and better multi-beam, these things will be even further refined, more accurate. This is looking towards the southeast, back towards this direction to see that. Here's this plunge pool. Now, a plunge pool is where a waterfall goes over a cliff and it hits, the rock or whatever. It makes a pool because where it grinds away the rock below. So this is a plunge pool at deeper than 1,800 meters. This is deeper than 6,000 feet underwater. So this plunge pool was not created by a waterfall, but it's created by these turbidity currents, which are the sediment-laden density currents that come from the Coronado submarine fan all the way down that meandering stream and come roaring down this channel. And they happen to overtop this ridge and create, a turbidite fall. And there's a plunge pool cut into the side of this scarp. And so that was one of our targets for the dive. So this is some data that we got after that cruise when I had the student cruise with Oregon with UC Santa Barbara in 2003 to map this area with high resolution seismic to show this is the sub-bottom image of the fault. There's the San Clemente Fault crossing the Navy fan. You can see the sediments here have been uplifted, and these pinch out because that shows that when these were deposited, they were flat, but now they've been pushed up. And then these are deposited, they were flat, but now they're pushed up. And that shows the history of this growing up as this fan keeps filling. So if we can get the age of those, we can get a rate for the uplift on the fault. Now, we also need to find a way to get the rate of the strike slip, because again, this is a vertical strike slip fault. Now, over here, you've got some more complex faulting, but you have to be careful because we had this circular track, and that's because when we were doing this cruise, we could only shoot seismic in the daylight so we could make sure there were no marine mammals around. And by the time we got ready, we were already up to here. So I had to beg the captain, can we loop around to get online because we've got to cross this fault scarp. He said, okay, we did. And that was actually, I was upset at the time, but I realized it was serendipity because by crossing this very steep slope at an angle instead of straight over, if this is straight over, you couldn't see the slope where it's too steep. But going at that angle, we could see the layers of sediments in that uplifted block, and we could see where the fault crossed. So that was a fantastic luck that we got that. So that shows that crossing here with very high resolution. This is only 100 milliseconds, which is about 75 meters. So these beds are probably 10 meters, which is about 30 feet thick or whatever. But, and that's pretty good resolution for underwater. Of course, on land, you can do inches and stuff, but this is really great. And of course, we have this to get the deep structure. So we are very happy about that. And this is what we found. Here's a mole track, a nice zigzag jaggedy. And you can see it's an older one because it's sort of weathered away here and some chunks had fallen out here. So this is an older earthquake that's covered, and you can see some nice brittle stars here. The brittle stars are all over the place down there. But this is a vertical scarp or near vertical scarp with a pile of rubble at the bottom, and that's 20 centimeters. This scarp is at least 2 meters high. So that's at least 6 feet high. And it really appears to be a single event scarp. You can sort of see, striations or lineations suggesting this is mostly strike slip, but there's some uplift. But these things we call chatter marks, you see this zigzag, a chunk of this part broke off in the movement and fell off, leaving that. And so that means this part was going away towards the right, and the part that used to be where we would be taking the picture moved towards Alaska. So that shows this was a right lateral strike slip earthquake. So here we have what every geologist wants to have. We have a smoking gun that there are large earthquakes on the San Clemente Fault. We're talking magnitude 7 or bigger. And that was a hard sell before we got this kind of data. But now I think after we've had the last 30 years of surprising large earthquakes on faults that were unknown or unexpected to have large earthquakes throughout the Mojave Desert and Baja and other places, is becoming more acceptable. But this is hard proof that that has happened on the San Clemente Fault. And for this young of a scarp, it's not that long ago. Okay, so let's try. Ken, I got to try to do the video now. So if I stop, do I want to stop share? Stop share. And I need to go to which? Share screen. We want to go click video.
So you all know this is a little experimental.
Share. Oh, share.
And we may
So
or may
we're
not
looking
be.
at an Alvin video, hopefully, with QuickTime.
There you go.
All right. Yeah, it should be.
You can get it to run.
What? Oh, there's two QuickTimes. Oh. Oh, that's an Alvin. Okay, that's one. Yes. I should read the instructions. It helps. Okay, can everyone see that?
There we go.
All right, so this, now it'll be noisy. And remember the movie Apollo 13? The CO2 scrubbers? That's the background noise. So just like you're on the moon and the bottom of the ocean, you've got to have CO2 scrubbers. So we're going down a fairly steep slope. There's a bunch of brittle stars. It's, you know, for a geologist, it's mud, so it's not real exciting. We're going along and and probably 90% of the ocean floor is like this. It's this mud, you know, with creatures and all different types, but not as many as in the rocks. But now all of a sudden, whoa, the bottom disappeared. This is a fault scarp from that last earthquake on the San Clemente Fault. And it's really important to show this with a video because you don't really get the scale when you look at that photograph. Because, you know, yeah, you can say that's 20 centimeters, 8 inches. Well, but now you can see, whoa, this is a big scarp. And here's some clams from some ancient seep deposits that have been uplifted probably several times by earthquakes. And it's still going down. And of course, you know, you don't just turn Alvin on a dive. You got to be careful of getting around and get things. You don't want to bump into it when you're going down. And you want to get you turn around to get a good picture looking straight on the scarp. And there's a lot of marine snow, as we call it, all these creatures and stuff coming from above that are floating around in the water. You can see here it's dropping down some more. And it's so steep, it's got to be very recent. And very recent, it's got to be probably within a few thousand years or less. We just don't have a historical record that long to know. And in the historical record, we don't know any earthquakes that large in this area since 1800 roughly.
I do love the fact, Mark, you say very recent followed by 1,000 years.
We've got to remember those earthquakes in the Mojave Desert have multi-thousand-year return periods, and we've had several of them in the last 30 years. So, and now you see, oops, we bumped into it. And this is mud. This is not rock. You've pushed mud up into a vertical slope. And you can see layers here. It's layered mud. These are older, probably Pleistocene sediments from ice ages past. And we stirred it up. And so it takes a very rapid event, an earthquake, to produce a scarp in mud. So this is, like I said, this is our smoking gun. Now, is that a holothurian? These are, again, I'm not the biologist. I know holothurians are common out there, the sea cucumber stuff, but there's a lot of interesting creatures. And there are seeps in the area. So there are vents of methane and other mineral water stuff. And you can see we really kicked up the mud.
Yeah, you did a good job on the visibility. It's like a new student on the first dive.
You can see the stratigraphy here. You can see the layers, and that if we can get the age of those layers, then we can work on uplift rates and try to get an idea of how frequently earthquakes like this might occur. So there's future work for students, you know, PhD and master's students. And I don't like to talk about the CO2 scrubbers with Joyce because she watches Apollo 13, and I said, well, you know, when you're in Alvin, you don't step outside for a smoke or whatever. You're in there and you need to have clean air. So there's the rubble pile at the bottom. And of course, the critters love the rubble pile. Lots of hiding places and some soft mud to burrow into in the cracks. And then over here, it's more of it's a less steep slope. It's not quite vertical, but this is still a pretty steep slope. You'd have a tough time climbing, especially in muck like this, you'd probably sink into your knees. Although in water, you're buoyant if you've got your weights adjusted properly and buoyancy cups. And again, you've got the vertical scarp here. And so we did several dives on this scarp, and we even went over to the plunge pool, and I'll show you a photograph of the plunge pool intersection with the scarp shortly. But this, this is, okay, this is a layer of clams. This is a clam bed from an ancient seep. And in a lot of these layers, you'll see these clam beds. So we could possibly get the ages of these clams, and again, get estimates of how quickly, how fast those scarps have been rising. Although if that's one event, it went up that much. So here's more of these ancient clam beds. And so really to do this right, we need the biologists to work with us and the geochemists, to get the chemistry and to get the age controlled. So it's a really multidisciplinary study to study these things in the bottom of the ocean. There's another clam bed. And these are buried clam beds. Okay, so that's the video. And of course, there's lots of videos from lots of dives, but we don't have time to show all those. So let me go back to share screen again. So I'm going to go back to. Okay, so just to refresh your memory, here's the pressure ridge, here's a mole track, here's a vertical fault scarp on a strike slip earthquake that was out at Hector Mine, Lavic Lake, 1999, maybe remember the 7.1. The scarp we looked at is at least that big. And it's got the same features, it's just that this is dry and it's saturated in mud. So we've had magnitude 7+ paleo earthquakes that may be found. Like I said, it's my smoking gun. So we are very excited about that. This is the plunge pool here, and this is the scarp, and you can see these striations, these grooves. That shows the direction of the slip, and it's almost horizontal, but it looks like maybe 10 or 15 degrees off horizontal. So there's some uplift, which explains the uplift of that ridge, which blocked the Navy fan to make it move around it and create a plunge pool. So that was very exciting. Now, having looked at this a lot of times and a lot of profiles, and you see this character, you got the main fault, but you've also got subsidiary faulting, especially when you have things being pushed up. And my sons and I went down to visit a friend, and at San Onofre State Beach in 1998 was an El Nino year, and we had a lot of rain that year, and several landslides that hadn't moved for a long time started moving again at San Onofre State Beach. And this one in particular was moving out with the toe of the base of the landslide under the sand, and the toe of the landslide actually in the surf zone just offshore behind this photo. But this edge of the landslide, here's the landslide moving towards us, and this is the beach which is not moving, and this is the fault zone. This is a strike slip fault zone, just like the San Clemente Fault. And here is your steep main fault, what we call the principal displacement zone, the PDZ, the San Clemente Fault. But here you've got these secondary faults, which are reverse faults, where it's shoving up slices of the sand over here next to it. That's a beautiful model of the faulting in the California continental borderland, because this is going on all over the place, and especially along these areas where you've got that compressional component, the Santa Cruz Catalina Ridge, Catalina Island, Palos Verdes Hills, and the Palos Verdes Fault. Now, if I have a big earthquake that does this and pushes up the water bottom, the water's going to move, and you might expect a tsunami. And of course, that tsunami would be minutes away from the beach, and the only warning you would have would be the strongest shaking you've ever felt in your life, unless you've been through some of these big earthquakes before. And I have friends that lived in Northridge, directly above the epicenter of the Northridge earthquake, and they know how bad the shaking can be. They said they were thrown 5 feet into the air when it hit, because they were directly on top. Anyway, so this is the type of structure, in a geological model, actually, at a smaller scale of what we see offshore. And this is a map view. This was a large earthquake in Algeria, there in North Africa, and this was left lateral. So that side's moving to the left compared to this side. You look across the fault, moves to the left, left lateral. But this one's right lateral. See, these little faults have this en echelon pattern, and they step to the right, step to the right, step to the right. So that's the left slip. But these step to the left, step to the left, step to the left. So that's right slip. And see, there's our photo. We were looking at that face. And that's the edge. That's the zone of the faulting on the edge of this landslide. And like I said, that's just a really nice analog model for the tectonics of the borderland. So we'll get back home here to Catalina. And here we're looking along the ridge towards the northwest. And just these are the rocks up there just past the airport. These are the serpentinite. These are the rocks which used to be upper mantle and very deep crusts that have been pushed all the way up here above sea level. And off to the left a little bit are those garnet amphibolites, which are very deep crustal rocks. These serpentinites are where you get the soapstone that the natives would use to carve their bowls. And you can just see the character of Catalina and the steep slopes. And there's landslides all over the place, especially at this end of the island in the schist, which is very slippery metamorphic rock. Catalina Island is a restraining band pop-up structure. It's pushed up by these earthquakes over millions of years. But the island is now sinking. And my colleague, Chris Castillo, who was a Long Beach State student, had done some work when we were mapping out here with Dan Francis at Long Beach State, mapping the subsurface features. I was telling him, yeah, there's a mystery as why you don't have those beautiful uplifted marine terraces on Catalina like you see at Palos Verdes. And I said, well, maybe they're underwater. And so he did that for his dissertation at Stanford. It's got his PhD. And after 2 years of fighting with reviewers, it was published. And the evidence of the island is subsiding is conclusive. But it's also tilting down to the northeast. This side is sinking faster than this side. And that means the Catalina Fault here is still lifting it up. And with my colleagues at USC, we modeled that for a tsunami source, which was published back in 2004. There's submerged marine terraces. So those terraces are underwater, and you have the landslide prone rocks from the subduction zone because of the schist. They're slippery rocks. There's a lot of clay and micas in them, which are just slippery. So this is an image that Jose Barrero made when we were doing the Catalina Island tsunami source, and it's 15 times vertical exaggeration. But you can really see you're looking sort of in the direction of the plate motion here. Catalina is clearly oblique, and that's why you have this big uplift. That's your big pop-up structure from that restraining band, and that's a big one. Here's Palos Verdes Hills. That's a pretty big one, but Catalina is a little bigger, more uplift. But this is also part of the Palos Verdes Fault Zone, this last one. No, and that's a nice sized one. And then along the Newport Inglewood Fault, all across LA, you've got all the hills, the Dominguez Hills, the Buenaventura Hills, all those hills. Those are all little pop-up structures because the Newport Inglewood has a lot of stepovers and bends as it cuts across the Los Angeles Basin. And over here's the Elsinore Fault, and it steps to the right, which creates Lake Elsinore, which is a pull apart a hole. But then you can see when it comes around here into the Whittier Fault, it's a restraining band, and there you go. You have the uplifted Whittier Fault and more uplift here. So this is the whole thing about restraining bands. If you got something that big, and a couple, 1,000 meters of water, and it moves up a meter or two, you're going to make a pretty good wave. Now, the evidence that proves Catalina is sinking was from the very high resolution seismic reflection profiles that Chris Castillo did for his dissertation. And most of the on-land terraces, like when you drive, well, you see them on Palos Verdes, those little stair steps up the slopes of Palos Verdes. If you go along the coast to San Diego, you'll see them, and they're wave cut. So they were eroded during high sea level stands during the interglacial periods when the water level was high. But during the low sea level stands, you have depositional terraces, and you can see these are depositional. These are like deltas. You've got sediments coming out. You can see the layers prograding. They call it prograding. They're moving out as it grows out, and they're growing on top of other ones, and they're growing on top of other ones, and they're growing on top of other ones, and they're growing. So there are more than one sea level stands in this one profile. This is fantastic data, and it shows this is more than 300 meters deep, and no sea level in the ice ages was that deep. So this has to have sunk since the ice ages. And the modern terrace is up here at about 120 meters. So that's about, 300 feet or so at the shelf break. So you've got terraces down here showing this island has consistently subsided, and this is on the northeast side, which is subsiding faster, tilting that direction. Whereas this side, and you can see these are terraces here. You can see the edges, there's a break and it slopes down, and there's another terrace and it breaks, slopes down on another terrace. And that's, again, that's for Chris, that's the smoking gun that Catalina Island is sinking. Now, of course, we're all concerned about sea level rise. And if the sea level rise because of climate, well, you've got double whammy at Catalina because you're also sinking. So it's not sinking that fast, but it's sinking fast enough that it's sinking faster here than the coast. And that should show up in the tide gauges probably over several decades. I don't know if that Okay, so this is some of the evidence we got from the dives with, this was on the Delta submersible. The Delta actually comes out of Torrance, and this is where the Oregon skate again. And this is at Pilgrim Bank, which is at the northern end of the Santa Cruz Catalina Ridge, south of Anacite Island, about 10 miles. And here is the wave-cut shoreline into basaltic, lava rocks, and the sand, which actually undercut. So that's the beach from 18,000 years ago, before sea level rose. And here, a little bit deeper, is the sand bed and shell hash bed, which was the surf zone for that 18,000 year shoreline. And here's another one of these beach shorelines. And so we've got those, and we saw other ones, this, 111, that's up here, 120, we're getting down to here. There was others down here, 200, we even got them down to 250 meters. And the Delta sub is limited to 300 meters, so we didn't get deeper. But on one of the deeper dives in Santa Monica Basin, I think Ken might remember this. We call it dandelion.
I was going to say a dandelion, right?
In 1996, right?
Yeah.
And they were first discovered around those hydrothermal vents on these Pacific rise. So they're thought to be related to hydrothermal activity. Well, some of these were out there in the Santa Monica Bay, but there's a bunch of seeps out there. So they may not necessarily be hydrothermal, but they do seem to be associated with seeps. And I was really excited when I got to see one here, locally. So they're more common than we thought, but they're still not as common as these other creatures, like brittle stars. Brittle stars are extremely common. So many of you may know this feature. This is Arrow Point. And Ken mentioned that at the beginning of the talk. And just around here, there's a little beach, and it's a popular dive spot. And Ken was saying they were diving here, and they were diving around here, and there's a sailboat and about 40 feet of water. And he said, whoa, they went back a week later, and it dropped down to 100 feet, from 40 feet to 100 feet, and the sailboat was on a cliff. And one of the divers says the sand was bubbling, and that's a very important observation. And this is data that was acquired in 2008 by Mbari with they were funded by the state to map the 3 mile of the state lands, in high resolution multi-beam. So this was data they did around Catalina in 2008. And lo and behold, there's the landslide that Ken and the diver saw in 2005. Now, 2005 was again another El Nino year with very heavy rains that previous season. And it took until September for that water percolating down. See the steep slopes? There's a big landslide here. And the groundwater follows the base of the landslide, which actually is under the ocean. And that water seeping out, they call spring sapping. And that water is what we think triggered the landslide. Because I checked the seismometers after I heard from Ken, and there were no earthquakes or anything in the area for that time. But the bubbling sand, I think, is for this, the smoking gun, that was triggered by that excess water from the rains. But here's another fairly recent one. We don't know when this one happened, but it looks pretty young because you can see there's the headscarp. You've got this narrows where it went through, and then it fans out here. And we don't know when that one was. It may have been the same time. We don't know because the divers weren't diving there. And here's one you can see which is much older because it's smoothed out by the currents and sedimentation. So this is a common place for submarine landslides. And I'm convinced, you see here's another landslide. So this is probably a landslide fed as well. So this is the water. But the other interesting thing, look at this channel forming here with maybe some levees and some. This is, a nascent submarine canyon. It's a brand new submarine canyon starting to form in thousands of years or millions of years. This may be a significant submarine canyon. And that's caused by this flowing here. And we think this flowed to the east because of the currents, the dominant currents maybe, but this one didn't. So we weren't sure, but I was saying, well, boy, if we could get down there and look at that, that would be great. Well, first of all, here's just a quick geology for the island. This is the volcano. So this is the Pluton. Here at Avalon, you can see these rocks there when you get off the ferry. And that's the core of a volcano a few miles underground, looking at the granodiorite. So that's the plug in the middle of the volcano. These are the Anacite lavas and the stuff that came out of the volcano. If you take the road from Avalon up to the airport, you go through in this area, these sheeted dikes, and you've got these vertical, they're like vertical lava flows where the lava that became andesite came from the granodiorite Pluton because it's the same chemistry. It's just this is big crystals, these are small crystals because they cool faster. They're squeezed up, one after another, like a bunch of dominoes as they come up and then come and flow out at the surface. So you're looking at the core of a volcano here, but all this green stuff, this is the schist. And you got green schist and blue schist, and it's slippery stuff. So you got some volcanoes over here too, out here by the Wrigley, at Big Fisherman's Cove. We've got the dike there, the dacite plug and so forth. So mostly this island is very rigid, but this is very slippery and very prone to landslides. All these black lines with depths, those are the marine terraces that Chris Castillo mapped for his dissertation. You can see there's a lot of them on that side of the island and down here, but on this side, they're much steeper, which is why he says this island, is still going up because this fault's still active. But notice the fault makes a big step here over to Little Harbor. And Bulrush Canyon, a student at San Diego State in Bulrush Canyon, actually found slickensides in a canyon wash along here in Bulrush Canyon, showing that that actually is an active fault, which then goes on to Santa Cruz Island. So that's the Santa Cruz Catalina Ridge fault. And that may have some effect on the canyon, the submarine canyon coming out of Little Harbor. So we talked about that landslide up here at Arrow Point, but when I got looking at the multi-beam data over here, I said, whoa, there's a big one. This is 1.3 cubic kilometers of material. It's about 1 mile across, and it left a 1 mile wide trench, although it looks like it may have multiple paths, that came a few miles down this steep escarpment. So there's a really big landslide. If that went fast enough, that probably made a really nice tsunami, a pretty good local tsunami. And of course, you say, oh, I'm over here, I'm safe on this side. Well, no, the tsunami wraps around both sides of the island, and when it meets on the other side, it's twice as big because the two waves come together. So you're not as safe on the back as you are anywhere else. So that was pretty interesting. So we went and take a look at that. And with Dan Francis, the Long Beach State professor, we were doing some studies in San Pedro Bay mapping the faults. But I said, Dan, we see this big landslide over here. Let's go do some seismic profiles. So we did one along the slide here, along the trench. You can see the trench here. And there's the landslide block where it stopped. And we went across the block, and then we came back to get another crossing. And here again, those terraces really show up in this bathymetry. And so here we are going down the slope. And so this is where the trench is, and that's probably new material that filled the trench. So this is older, maybe thousands of years old, we don't know. But this is the block here, and it stopped at a fault. Here's a fault where this side went up. See, that went up, and that went up. And that seems to have stopped the slide. But there's another fault here that cuts through and even deforms the back of the slide. So that may be a more recent earthquake. But it's possible that this big landslide was triggered by this large earthquake thousands of years ago. We don't know the age because we need to get the age of these sediments, which is not easy. But maybe here we could actually take samples where this is exposed and get an idea of when this happened. But that's a very big landslide. And that, from our experience modeling tsunamis at USC, the Tsunami Research Center, Kostas Sinolakis in the group, that would make a pretty good tsunami. And this is just a close-up again showing this is the slide block, and there's some details you can see. Things are pretty, it stayed very intact here, but then at this end where it crashed into the uplifted fault, it sort of got crushed, and you can see the deformation in it. And you could even see boulders here. And this dark stuff actually may be younger sediments that's just draped on top of it since this happened. So this may be, like I said, this may be thousands of years old. We don't know. And this is the cross section again. There's another view of where he did seismic profiles. And there's another one over here, not quite as big. There's the trench and there's the block. So we have big landslides offshore that can make tsunamis. And maybe they're triggered by earthquakes, but we know the one at Arrow Point was triggered by rainfall. We don't know how big a rainfall triggered one could be. But, and like I said, Catalina Island, it's a very, very famous spot geologically. It's known around the world because of that exotic geology. It's exposed the core of a subduction zone. It's exposed the core of a volcano. So a lot of geologists from around the world come here to study the geology. Well, it now may be going into outer space because these are astronauts that NASA had come out here. This NEMO Next, it's a NASA Extreme Environments Modeling Operation or something like that, because they were working, underwater at Key West. But there aren't any hard rocks at Key West. It's all coral and limestone. And so they said, well, you got to go to Catalina. That's where the good rocks are. So they asked me to come and point out some hard rock streams. So this is the Japanese astronaut. This is the Belgian astronaut. This is Drew, who is our American astronaut. And I think these are the two of the NASA people that were along helping. One's a geologist and they're running this program. And this is the surgeon who works with the Japanese astronaut. These guys are really, really really good guys. And you can see here in the background, there's the Wrigley Center at Big Fisherman's Cove. We're on the pier. And there's some underwater equipment here. And I think this is Drew here, suiting up to go in the single man submersible, because they're doing operations here in Big Fisherman's Cove. Because, in space, you're going to be in a spacesuit and you're going to be sampling, and you got to know how you can maneuver to pick up things in space and look for. And so they were doing these underwater operations too. So that was pretty cool. So it may be going into outer space now, and I think that was great. So just to conclude, this active faulting, it's all over the borderland, and it's right along the coast. And as you may have seen in the news recently, there's a new interpretation of the Palos Verdes Fault and how big the earthquakes are. And there's a lot of new interpretations of how big earthquakes can be in Southern California, because the last 30 years of the Southern California Earthquake Center, since it was formed in 1991, we've had several large earthquakes in the Mojave Desert in Baja California and overseas in Kaikoura, New Zealand, and so on faults that they didn't expect to be active or didn't know they could have large faults, and they ruptured more than one fault. They were very complex. So now the scientific community realizes large, complex, multi-fault earthquakes can and do happen. And so they can now accept the fact that these complex faults, like we see offshore, can have large earthquakes. And so that new paper from Harvard is just another model. I have my own version of the model, and I worked with the guys in Harvard, and we have some differences of opinion, but I think we're both right, because as I was showing you, we have the combination of the strike slip and the compression, the transpression, where other places we have the extension where you pull apart a basement, but we've got major ridges like Catalina, which are being pushed up in large earthquakes. And it's that combination of complex faulting that we need, to look at, both those kinds of faulting and model those. And so hopefully together the scientists could come up with better models, and we can get data offshore to find out how often or how fast these faults are moving and how frequent we can have these large earthquakes. And we saw these pressure ridges with mole track. And I think, pressure ridges are just mole track accumulated over multiple earthquakes, thousands of years, maybe tens of thousands or hundreds of thousands of years. But lots of scarps, linear valleys, and seeps, and the seeps are of interest for the minerals coming out, and the manganese nodules are of interest because there's a lot of manganese nodules out there. And of course, the oil, the seeps are related to the methane coming out as well. Landslides are all over out there, especially in these soft schist rocks and on the sedimented slopes. And the offshore can be triggered by rainfalls, we saw at Arrow Point, and they can be triggered by large earthquakes. So we need to be prepared, be earthquake prepared, but enjoy it, because it's a beautiful place. And for a marine geologist, it's really a very exciting place to study, because it ain't easy. It's a challenge, but it's really fun when you discover things and find a smoking gun to say, hey, I was right about that. So I think that's it. Any questions? I'll try to answer.
Mark, go ahead and hit stop share.
Okay.
So we can, there we go, get everybody back. And then we'll give you the traditional applause. Thank you for the presentation. And then what questions do we have? By the way, just so you guys all know, before you're going to be allowed to leave. There is a written test tonight on this one. So and hopefully you were taking notes and paying attention. So,
and it will be graded.
yeah, I'm sure it will. Either just physically raise your hand or use the raise hand icon if you have anything, or Glenn, I can always count on Glenn to start us off.
Yeah, sure. So your theory is that there is a difference pulling apart of the land zone between the islands, essentially, and the mainland, and that would essentially what make the crust like the crust thinner, or where the zones are in opposite directions. Okay, so you have the fault line going north and south, and then you're saying that there's some forces that are counter 90
Okay.
degrees to the.
I understand your question. What's going on is 20 million years ago, when the East Pacific Rise reached the coast and we went from a subduction zone where things were being shoved underneath, the Pacific plate has always been moving away from North America. So the first part of that tectonic evolution, starting about 20 million years ago, was to pull the part of North America that captured, which was the subduction zone, those two zones which became the transverse ranges and the outer borderland. It pulled those away, okay? And that was going on 20 million years to about 6 million years ago. And then 6 million years ago, the East Pacific Rise finally reached the tip of Baja, and the Gulf of California started opening. So the opening shifted to the Gulf of California. So that opening part is mostly ceased for the borderland now, for California. But in the meantime, I don't know if you've seen that theory, the transverse ranges were originally, parallel to the North American coast going towards Alaska, but they were caught in a corner and they rotated into their position now. So they're, they're east-west now, but when they became, perpendicular to the movement of Baja trying to get through, things started to really get stuck. And so now you created a lot of compression in that area, this collision, and they continue to rotate, but that collision is happening now. And what we see in detail, the transverse ranges went up. They went up very fast, and they're only like 1 to 2 million years old. So those mountains, like the Himalaya, came up very fast. And you go up to Big Bear, and you can see how deep those canyons are, how steep, because those are very young mountains. Meanwhile, that wave, the compression, sort of works its way to the south. And it's gone about as far south as San Diego, because my thesis work was south of the border. And in Mexico, there's still extension. It's not as fast, but you can still have extension on some of the faults. And that's partly because the fault trend for the San Diego Trough Fault is more to the north than the plate motion. So the plate motion's like that. So when the part west of San Diego Trough moves, it's still creating some extension on the San Diego Trough Fault south of the border in the southern borderland. And there are volcanoes down there that have been active. Well, San Quintin, if you've been in Baja, that's a Holocene volcano. So that's erupted in the last 10,000 years or so. And there's young volcanic rocks in the southern borderland. So again, this is a very four-dimensional problem, and that's part of the fun, but it's a real challenge. Does that help?
I mean, I think, Mark, part of the interesting thing is we think of the San Andreas Fault, and we probably heard of like the Inglewood Fault and a couple of others. But then you see your map, and there's like 8,000 other faults there, and you go, holy crap, there's more going on here than we thought. And it seems to me a lot of times, I may have this wrong, but I want to say with the Northridge Fault or Northridge earthquake in, 94, everyone's saying, oh, this happened on a previously unknown fault or a fault we thought was inactive or whatever. So it's like, there's an awful lot of crap we don't know, it sounds like.
welcome to the real world.
We don't like the
Yes,
real world.
There's a lot of stuff we don't know. But you know, the trick with Northridge, and you may remember Loma Prieta in San Francisco, the World Series earthquake, those were on blind faults, the blind thrust faults, which is what the Harvard group specializes in studying those. And those faults don't reach the surface as a fault, but they push things up, like the Santa Cruz Mountains, like Palos Verdes, and even Catalina. But those faults at Catalina now surface underwater, and technically underwater faults for most of us are blind because people weren't looking there. But it's not simple. The Earth, when you think of a complex geologic evolution, when you had subduction, you had deep rocks and you had compression and sediments and stuff, and then you pulled up those deep metamorphic rocks, which are now exposed at Catalina. They're very dense and very hard and very slippery. But on the other hand, while you did that, you opened it up, like we were saying, and you had volcanoes, and Catalina was a volcano. So yes, it was heated up because you thinned the crust and the mantle came up because the East Pacific Rise had just gone by. And so now you've got volcanic rocks in there. You had those huge super volcanoes in the Miocene, and these are all over the place. So it is obviously very complex because there's faults associated with all those features, and new faults can form, but new faults in general, the Earth prefers to use an old fault if it's reasonably oriented rather than creating a new fault. But one example of a possible new fault is the San Miguel Vallecitos, which comes from, there was an earthquake in 1956 in northern Baja. It was a 6.8. And you remember the seismicity, there's humongous amount of earthquakes in northern Baja. And that earthquake trends towards San Diego and goes through what's called the Vallecitos Fault, which had been mapped in the mountains. And of course, right under Rodriguez Dam, south of Tijuana, of course, they built the dam on a fault, but because there was a valley there. But that fault may be a very young fault because the San Miguel earthquake, even though it was 6.8, the slip wasn't very much. And the geologists who went and studied in detail, the total slip on the fault is only a few hundred feet, or maybe a few hundred meters. But that's nothing compared to what 300 or 600 kilometers or 300 kilometers on the San Andreas or 60 kilometers on the San. So you can get new faults, and I think this is the problem we have. The Baja California microplate is ramming into the transverse ranges, and it's trying to get around it any way it can. It's trying to get the San Andreas, it's bent around it. It was offshore, but the offshore couldn't get around it. And so the San Jacinto is trying to get around it. The Elsinore is trying to get around it. And now we have the Eastern California shear zone with the Ridge Crest earthquake. And in 1872, there was a very large earthquake in Owens Valley. So it's trying to get around it that way. But when it gets around it, now you've got to get past the Cascades to get back to the Pacific plate. So it's a mess. We've got a complex bunch of blocks smashing together, and it's taking whatever the path of least resistance. It's
a whole lot of shaking going on.
Yeah.
Any other questions? Glenn, do you have another one forming on your brain?
Well, sort of. So
I saw the steam coming out.
Yeah, I know. So in your opinion, what is most important for civilization? Let's say, we have all our population living on the coast, and specifically in this area where everything's coming together and dynamically fighting with each other, so to speak. So where would you like to see the research, and what do you think might be the outcome or from that research?
Well, the one thing, we cannot accurately predict earthquakes. And so like people doing the weather, we try to forecast earthquakes. And so the Southern California Earthquake Center, USGS, and others around the world actually are trying to better forecast earthquakes. But of course, the number one thing is to be prepared. And we have good engineers, and there's a lot of buildings. When you look at an earthquake and see all the damage in areas where buildings are built properly and tied together and good foundations, they have minor damage. So you've got to make sure the building codes are enforced. And, I know from working with structural engineers, details matter. And so you've got to make sure that they are enforced, and that, when the design may be great, but if the construction, they cut corners, like I heard stories of houses in Northridge where they hadn't put all the nails in the plywood wall, so the shear wall didn't work. So you've got to make sure, that you dot your I's and cross your T's and be prepared. But we can survive earthquakes and we can survive tsunamis. But again, if you build a dam on an active fault, or if you live at the coast on a cliff which is eroding even just from sea level rise and coastal erosion, you better be prepared to have to move when the cliff fails. Because I saw that in 70, 78, storm years when I was studying sea cliff erosion with Francis Shepard and Scripps in San Diego. We saw 110-foot section of cliffs go down one day. The guy had just gotten off the steps, gone to the ocean when he heard the rumble. But these things happen, so you've got to be sensible. But we're also, civilization, population continues to grow, and everybody wants to live near the coast because it's a great place. It's cool and comfortable and beautiful, and in the mountains and in the woods and all these. And so we just have to understand the risks and do our homework and be prepared. And there's lots of activities where you can go, your earthquake preparedness kits and all these sorts of things. And because I was involved with the Tsunami Research Center when they did the inundation maps, and to get people to know, at least with a tsunami, if it's distant, you have warning time. If it's the local tsunami, it will be the shaking. But fortunately, the major faults, well, most of them are far enough offshore, you probably will have several minutes or maybe 10 or 15 minutes warning. But if it's on the Newport Inglewood Rose Canyon, or right along the coast, you only have a few minutes. And so these are serious issues. And things that I've been thinking about a lot lately is for responders, because the firemen and the responders need to get out there after the earthquake to start cleaning up. But if a tsunami is coming, they need to have an idea. Okay, I know from the tsunami research, there's not just one wave. And the first wave is not always the largest. We saw that in San Diego from the Tohoku, because I went down and talked to the boat, the harbor police. And they said, yeah, we had everyone here Saturday morning, 9 o'clock. The tsunami came, nothing happened. So everybody went home. 4 o'clock in the afternoon, whew, the currents came in and they were amplified there by the shelter island, and they'd lost a couple of boats. So the docks were damaged. But those things are replaceable. People, need to know when there's a tsunami, you take it seriously and move to high ground. So preparedness.
Well, boys and girls, we've reached actually past the magic hour of 9 o'clock. So I think we again give Mark our traditional Zoom Seekers round of silent applause there. Jeff's just doing it with the one hand there. That's fine. And I don't know who Best Mommy Ever is, but I've been watching this shot. That's her wine glass. I think her phone's just sitting down on the table, just catching. There you go, catching the wine glass in the light. So anyhow, no problem. And that wine glass was a lot fuller about half an hour ago. I've noticed that too. Not that we're watching your drinking or anything like that. Next month, the date is November 8th, and I don't know what it's going to be. I had scheduled Dr. Sam Miller, who's been around like forever, who unfortunately died a month or so ago at the age of 91. So he led a great life, but unfortunately will not be around to share it with us. So I'm not yet sure what we'll be doing in November. I will have just returned from Indonesia, so maybe we'll do some Indonesia stuff, or we'll do an open forum, or I'll find a replacement speaker or something. So keep an eye on your emails, and we'll let you know. We'll let you know what's what. But that'll wrap us up for this evening. Mark, thank you very much for being with us. By the way, when I did one of my prized possessions, this is when I first met Mark. When you do the dive in the Alvin, they hang a basket on the outside, and they have these about regular large size coffee cups, and they doodle on them and stuff like that. And obviously the pressure crushes the coffee cup, and so they give that to you as a souvenir. And that's how big it gets. And so that's mine mine from the Alvin. The captain draws that up, and they have a little diagram of the Alvin on it and the date of the dive and everything else. And he signs it on the inside. So every day that's in my bedroom. Yeah, there you go. Mark's got his as well.
I got a couple.
Yeah. And what's
They
funny
say
is that the chamber, I won't say this is what inspired it, but Carl will take these styrofoam heads and they shrink the heads down as well. So, but this was 3,700. Well, I'm getting, that's from 3,700 feet. They say after you pass about 300 or 400 feet, it probably doesn't get too much smaller, but anyhow, good stuff. At any rate, join us on November 8th, and who knows what the hell it will be. It'll be a surprise, and we'll see what's what. You can all tell us about what great candy you got for Halloween or something like that. So again, Mark, thank you very much. Thank you guys all for spending time with us tonight on Zoom Seekers, and we will see you in November.